Thank you. Can you guys hear me? It's a pretty small room. Probably don't need the mic at all. Um, so, so I'm going to talk about some research that is not going to make a huge dent in the universe, but it was a very interesting experiment. We had Matt and Alex help us this summer, and we had a germ of an idea, and these guys were able to create something really awesome out of it. So before we get to what they did, we need to take a step back and really think about the DNA of a vulnerability. So if you do take that step back, a vulnerability is really a set of events that happen in an application. So for instance, you get a request parameter, you append some stuff to it, the data bounces around, maybe it gets put to a bean, maybe it bounces around the service layer, and eventually that data gets to a dangerous sink, right? A place where untrusted data should not go. So in this case, this is going directed to the user's browser. So this is a cross-site scripting vulnerability. So, whether you're using a static analysis tool or a runtime analysis tool like the one I work on, this is what a vulnerability really looks like. So what you don't see here in this list is the presence of a security control, right? And so that could be for one of two reasons. It could be because no security control was invoked, or because a security control was invoked, but the tool didn't know it, so the tool didn't recognize it. So that's the difference between a false positive, which is the bane of our whole existence as vendors, versus a well-reported finding. So rules come preloaded with a lot of the tools that you get on the market today. So it's possible for cross-site scripting to come preloaded with a set of controls like the AppSecUSA control. There's a couple other OWASP encoders. The Apache Commons library has a bunch of encoders. So we can kind of solve that problem for the most part, but there's still always going to be cross-site scripting controls that come from your packages, right? Your custom code. That's how you solve the problem. So so this is a big deal, right? Because there's currently not a great way of automatically detecting these encoders or security controls in general. So so again, I work on a tool called Contrast. It's a runtime analysis tool, meaning you install Contrast on your server, and it just kind of passively sits there, and it detects vulnerable code paths as they get exercised. So it's not because it's not a static analysis engine. It's really sitting in the app as it's running. We can't afford to be really using expensive static analysis to try to find these controls. So what I needed was a very fast funnel that I could run all the bytecode that gets loaded into the JVM, and I needed a fast filter that could tell me quickly recognize any encoders that went through there. So basically, this would allow Contrast to detect your security controls as they get loaded, and thus we wouldn't send you false positives because we didn't know about that control before. So those were the requirements that I gave to Matt and Alex, and they're going to tell you about what they came up with.
Okay, thanks, Arjun. I'm just going to jump right into what we ended up doing. Basically, what we ended up with was a two-step process. And the first step in this process is a very fast, single-pass analytical tool that goes through the methods essentially without any contextual information and uses a simple set of heuristics to figure out what the chances are that they're encoding methods. And then we use those heuristics to divide them into groups and move on to the next step. Now you can see at the bottom here a really good example of what we didn't want to do. We're keeping it simple. It's nothing complicated at this step. Second step, once we've divided everything into groups, we want to verify whether we've actually found encoders or not. So what we do at that step is we take the methods that we've identified as candidates, as sort of likely encoders, possible encoders, and we use fuzzing. So we send in a bunch of potentially dangerous inputs with characters that we'd like to be encoded if these are in fact encoding methods. And then we test the outputs and see what comes out, see if it's actually encoded the strings that we send in. So to sum up, basically in the first step, we generate a score, 0 to 100, for each of the methods that we're looking at. And we generate a separate score for each encoder type that we're searching for. So far we've got HTML, XML, and JavaScript. So it'll generate 3 separate scores for each of those types. Then we use those scores to, again, cluster the candidates in groups, and then we see what happens in step 2. So getting specific again, looking at the how we do the heuristic test in step 1, because that's sort of the meat of a lot of this. We basically did this on one guiding principle, and it's a phrase that you've probably heard before. If it looks like a duck and it quacks like a duck, it's probably a duck. The idea being, we're not trying to catch methods where people are trying to fool us, or catch methods where they're using really unusual algorithms or systems. We're just trying to find all the things that look like encoders, that really seem like, they're built the way encoders are usually built. And we found that we catch a really large percentage just by keeping it simple. So what we wanted to think about is, what distinguishes an encoding method? What are the things that it has to do? What are the things that it often does? So what can we use as heuristics? The first one that we came up with is string iteration. So this is pretty logical. If you want to have an encoding method, it has to be a string iteration in some form, because it has to go through each character in the input string and determine whether it needs to be encoded, whether it's a dangerous character. So we looked for a bunch of Java methods that sort of indicate string iteration, or equivalents like string.replaceAll as a method. We also looked for things like the creation of a string builder object, and then the use of the string.length and string.charaat methods, because that sort of indicates that some iteration is being done on strings. So you can see an example of that here. This is an HTML encoder. It essentially goes through and calls replaceAll for every dangerous character that it wants to encode, and then returns the result. So that would qualify as string iteration. Here's another one. It creates a string builder, and then iterates through by calling length, and then by calling charaat for each character, and again, just builds the string in the string builder and returns the result. So both of those would come up positive for our heuristic of looking at string iteration. The second one is we looked at whether these methods load certain constants that are going to be used for encoding. So for HTML, if you want to encode things, you need to load those things to do checking against. So in HTML, we look for quotes, less than, greater than, ampersand, and similarly for other encoder types. So again, we've got the same example from last time. Those are the string iteration indicators. And these are the indicators that it's loading those constants. So again, if we look at this method, you can see just from those 2 features, this is very likely to be an encoder. And even if there was nothing else telling us it was, we'd classify it as being a very likely encoder just from those 2 things. The third heuristic almost seems too simple to be effective, but actually we found that it was one of the most effective things at finding which methods were encoded, and that's naming. So most people are pretty conventional with the names they use for encoding type methods. We look for several different words that are often used, obviously encode, and then escape, normalize. Several others are used in the vast majority of encoder methods. And then additionally, we looked at class and method names to see whether the languages or domains that we want that encoding is being done in for that specific encoder type were used. So you can see examples again down there. That first one is probably going to be an HTML encoder because it has HTML in the class name and the method is called encode. And similarly for the second one, we have a couple of instances of XML and escape. So again, that's a really good indicator that we found an encoding method, and when combined with the other heuristics, it works pretty well. The last one is we looked at the signature of the method. So essentially, we drew a hard line in the sand. We said, we're not going to count anything as an encoder unless it takes a string as input. And there are going to be some really unconventional styles of encoding that we're going to miss as a result of that. But we decided that was a price we were willing to pay because it really reduces the search space we're looking through. And as we looked at it, it was a very small number of the methods that didn't have a string input. So that's one. And the other is string return value. And that we just counted as another heuristic. So we would count some encoders that didn't have a string return value, though it would be less likely. Those are encoding methods that do encoding, and then rather than returning the string, they store the value somewhere else for use elsewhere in the program. So here's an example of that, pretty simple. HTML encoder takes a string in, returns a string. All right, so once we've got our heuristic data, which we get by using the ASM bytecode library to go through each of the methods individually, then we use the heuristics that we've taken out to calculate a score for each of these methods. And what we say is basically, if it scores 0 to 59, and the scores are all out of 100, we say no, it's not an encoder. 60 to 79, maybe we want to look at it further, and we're going to send it to step 2 and see what results we get out of that. 80 to 100, yes, that's an encoder. My friend Arshan is going to stake his reputation on it. We're pretty sure. So then we get to step 2. We only apply this to, again, the top 2 groups from the previous step. So if it scores 60 or above, we're going to do step 2 on it. Essentially, the first step is to weed out the vast majority of methods and reduce the number of times we have to use this, which is a very time-consuming process. So we also further narrow it down by saying we're only going to take methods that have a single string input and a string output. And the reason for that is just that when we're doing fuzzing, we still have to send in specific inputs to actually to figure out how to get meaningful data out of it. And if we have complicated input types, then it's sort of hard to figure out for sure exactly what's going to be meaningful there and how that's going to work. The other thing is that we don't want any method calls in the methods outside of basic Java methods. The reason for that is if there's custom methods, we would have to rebuild those also, and that could get very complicated very quickly, especially if they're calling other methods, etc. So once we determine which methods we're going to rebuild in step 2, we use ASM to rebuild each of them in a new class. The reason for that is that we don't want to have any unwanted side effects in the host system. In contrast, this will be running sort of within the host system, and so we don't want to actually just call the classes in place because there might be unwanted side effects. And then all the methods are fuzzed using Java reflection libraries. So we use those to send in a bunch of strings, and we look at the results to see whether the strings we send in have been encoded. So this is an example of what a rebuilt class would look like in the bytecode. Just an example. And this is what the output will look like. So this is essentially from the whole process. So this is a method we saw earlier. It's an XML encoder. As you can see, it scored very highly for an XML, a little bit less so for HTML. It did get to step 2 successfully and was rebuilt and run. And you can see at the bottom the characters that we found to be encoded based on step 2. So that's based on the results of the fuzzing. It encoded all of those characters. So those are most of what we wanted to see for an XML encoder. And so we'd say that this is, to a very high degree of certainty, this is an XML encoder. Okay, so that's sort of what our method was and a little bit of how we're going to present results. So the question is, did we succeed? And we also want to ask, how are we going to define that? As Arshan mentioned earlier, for the purposes of contrast, we wanted something that was very fast. Obviously, we wanted to correctly identify encoders, but there are also some more complex things that we wanted to get at. One of those is we wanted it to be able to determine how complete an encoding method was. So if it's an HTML encoder, does it encode enough that it's a safe encoder for HTML, or does it leave things out? Same for other types. And lastly, of course, we don't want it to disrupt the system. Again, that's the reason for building new class files rather than running it in place. All right, so the tests we did were run on a local repository. This is a subset of the libraries in Maven. We ran it on 655 libraries, just over 100,000 classes, just under 1 million methods. You can see just sort of some output from the search process going on there. So speed. Arshan really wanted me to take that animation out, but he was probably right. Anyway, our test on those 1 million methods pretty much completed in an average of 16 and a half seconds. So that's somewhat over 50,000 methods searched per second. So for our purposes, that was fast enough. It's fast enough to run inline with contrast. And for any other sort of runtime applications you might have, that's a pretty fast speed. The other thing is, even if you're doing static analysis, it's not bad to have something that runs that fast. As we were doing testing, we found that it was nice to be able to change our search space a little bit or change our parameters a little bit and come back and have new results from these 1 million methods in 16 more seconds, rather than having to wait a while longer. So that raises another question. Obviously, in anything like this, there are trade-offs between efficiency and accuracy. So the speed at which it runs might make you think that it's not too accurate. And obviously, that's always going to be a little bit of a problem. So let's take a look at how we did accuracy-wise. Again, there were out of the million methods, about 400 scored over 60 on the original heuristic test. That's the first step. Of those, 113 scored over 80. So again, the over 80 methods are the ones that we're saying we're sure these are encoders. 60 to 80, we're not sure, and in fact, a lot of them turned out not to be. But those are worth testing just to make sure and find out. So our results were all the methods that scored at least 80 did some form of encoding. Now, what does that mean? It doesn't necessarily mean that each of those methods was an encoder of the type we looked for that was complete and that did everything we wanted to. What it means is that it encoded at least some of the characters we expect an encoder of that type to encode. So if it was HTML, it might have encoded ampersands and less than signs. If it was JavaScript, it might have encoded new lines and quotation marks. It at least did some of the right encoding. But there were some issues. We found that several of the encoding types were fairly similar in what they did. So HTML and XML do a lot of the same things. And so those were sometimes conflated with each other. Similarly, JavaScript encoders sort of generally do a lot of the same things as any encoder for sort of C-style strings. So we had a couple of cases where, for example, encoders that were looking at manipulating Java strings were counted as JavaScript encoders. We wanted to have some sort of specific criteria for success for sort of what it would mean for something to be a complete encoder of a certain type. So for HTML and XML, we said if it encodes less than signs, greater than signs, and quotation marks, that's a complete encoder, or we're gonna count that. And for those, the success rate was very high. It was over 90% of the ones that we said were, of the ones that we found to be encoders, the 80+ range. JavaScript, not so much. There were a couple of reasons for that. One was, as I mentioned, sometimes we conflated other types of encoders that worked in similar spaces with JavaScript encoders. So again, C-style languages with ASCII escape sequences. And the other reason was that a lot of the JavaScript encoders we found actually weren't all that complete. They were intended as JavaScript encoders, but they didn't necessarily encode enough characters to be safe tools. So we'll see an example of that. Here's an encoder. As you can see, escape JavaScript. It's intended to encode JavaScript. It has this list of characters that it's going to replace. But unfortunately, it doesn't necessarily replace enough to be safe. So you'll notice that less than signs and slashes are not encoded here, forward slashes. And so you can have something like this, where an attacker can actually escape from a tag, start a new tag, and essentially execute arbitrary code in that space. So that's an example of something where we would have found it, and the heuristic search would have said this is an encoder, but in fact it's not an encoder that's complete enough to be safe. All right, so that's a little bit about sort of the false positives we found, the things where we found where we called things encoders and they were sort of incomplete or a different type of encoder. The other question you might ask is, what are false negatives? In what cases did we not find encoders that were in the search space? The answer to that is a little bit difficult to say. What would really have helped us in this situation was if we had some type of tool that could search through a really large database and tell us quickly and accurately what the encoding methods were. Unfortunately, that's the tool we're trying to build. So it was somewhat hard for us to get definitive results here. What we did do is we looked manually through a couple of libraries, the Antler and the JSON libraries. And we found that we didn't have any complete false negatives, but we did have a couple of methods that scored between 60 and 80 that didn't fit our criteria for rebuilding. So those methods, in a situation like contrast where we need a yes or no answer, we wouldn't have been able to call those encoders, and so we would have missed them. But they were in the list of 400 out of a million methods that are in our list of possible encoders. So for static analysis, it might still have been a helpful result. Another way of looking at the false negatives question is to look at step 2 of our program. So essentially, if we look at methods in the 60 to 79, 60 to 80 range, are they actually encoders? When you do fuzzing, do they return the results that encoders would return? And this graph gives you some of the answers to that. So again, that left column is just sort of a reprise of what we saw before. 113 methods scoring at least 80 on the step 1 test. Of those 78, we were able to rebuild. And of those 78, 77 actually came across as encoders. The one that didn't was an HTML encoder, or an attempted HTML encoder that only encoded less than and greater than signs and nothing else. So we didn't call it an encoder, but it was at least attempting to encode HTML. And then from the 285 methods that were between 60 and 80, 100 were able to be rebuilt, and 10 ended up showing up as encoders through fuzzing. So then the question that we want to ask then is, why did we miss those 10? And more broadly, why did some encoders show up in the 60 to 80 range when we'd obviously like for them to show up in the 80 plus range? And the answer is that, well, our heuristic test isn't perfect. We can't get complete data on the false negatives, but we did see a couple of types of encoding methods that we can see for a variety of reasons that we can't catch with this. So method pairs of this type. This first method up here iterates through an input string and calls the second method for each character. The second method then looks at that character and encodes it and returns the encoded value. So we can't catch this because the heuristic test looks at each method context free. So it doesn't know what that other method call means. So it can't determine for sure if that first one's an encoder. One useful thing though is that just based on the fact that this does string iteration and based on the naming, it will recognize this as a possible encoder. So just based on those couple of clues, even though it doesn't really understand the full picture, it can at least say this is something that we need to look at further. Another example would be something where the encoding that you want to do is stored in a map. So it'll be a map or a table linking characters to their encoded values. And again, the method iterates through, and for each character, it makes a call to the map and returns the encoded value if it needs to be encoded. And we can't find that for the simple reason that we're only looking for direct loads of characters in the methods. And this is something that probably we could fix in a future version of this, much more easily than the first one. We need to have some way of looking at the characters that were loaded into the table, but those might be static, and so they might be pretty accessible to us if we just added a couple of things. All right, so to sum up, we basically created two separate processes that neither by themselves is exactly what you'd want out of a tool like this. But putting them together, we were able to achieve a bit of synergy. The heuristic search, step one, is fast and surprisingly accurate. But when you're talking about security, surprisingly accurate isn't necessarily good enough. You need it to be very accurate. And it also doesn't give you quite enough data on what types of encoders you found, and also on exactly what characters are encoded in the completeness. The second step, fuzzing, is pretty much 100% accurate, but it's very slow. And if we tried to run it on all million methods in the database, we would never finish. So essentially, what we have is something where if you put those two together, it's a pretty useful tool. And that's what we have. And I'm going to turn it back over to Arshen for summing up.
Yeah, so I knew I shouldn't let you keep that sprinter in there. I let you have to duck. And that wasn't good enough for you. So I think we learned a lot from this experiment in that we can do a lot with cheap heuristics. So I think the IBM tool uses a SAT solver to do something similar, and it's like, you needed a SAT solver? Like, this is the dumbest thing we could have come up with, and it was really effective. So I think we need to think more about using these heuristics. So just trying to expand on this idea and figure out maybe we can identify other types of security controls with similar data, right? So when I statically analyze a method just with a single pass, we get all these pieces of data: call depth, method frame depth, etc. So what I want to do is I want to go through a very fast experiment where we see we go through a method that I just pull out of the ether, and we look at the attributes for that method and see if we can't deduce what type of method it is.
What are the possible use cases for this?
So we're using it for our security tool to find security controls so that we can smartly apply our rules to them. And I think that's what other people.
Do you run it at runtime?
That's what we did is we baked this to happen at runtime. So we see if it's a good method for testing. We fuzz it, make sure it's a good method, and then we add it to our rule set dynamically.
But you don't run this in production.
No, this is a tool meant to run in QA or a developer desktop. So let's pull a method out of the ether and look at some of these things and see if we can't figure out what type of method it is and see what the higher level behavior of it is. So the call depth of a function is, how deep does this function go? At most, this is a call depth of 2. So at most, it calls a function and that calls a function and that's it. So it's not very deep. So let's look at the frame depth. The frame depth of this method is 3, which means it's not a very deeply nested function. It's not super complicated, not a lot of logic and loops and stuff. The method size, 58 bytes, relatively small. The method name, debug, maybe that means something to the heuristics that we're building. What are the parameters? A string and an object ellipse thing, which means a variable number of arguments. So maybe you're trying to figure out maybe what type of method this is, what type of security control this is. So what are the methods that it invokes? Message format, format, and substring. Is this a private method? Is it a whatever? So we check, and it's a public static method. So another thing that, a feature that these guys built into the scanner that they built was they've detected a higher level behavior by looking at a combination of the functions called. So they could tell that a function iterates over strings by checking if it calls get cars or some other functions. So by the presence of multiple methods, you can determine this higher level behavior. So we've identified some higher level behaviors that may be tipping us off to other security methods. So does this method iterate over strings? No. Does it update a message digest? No. So this to me looks like is a candidate for a logging method. Because it looks like it takes maybe a variable number of things. It's got the name debug. It's not very big. It does some formatting, and it's meant to be consumed by everybody. So this makes sense to me that this could be flagged as a possible logging method. So we ran this test on a very small subset of the central repository, Maven, and we got really great results. So I want to encourage people to start thinking more horizontally like that. So when I say horizontally, I think most of the industry we're focused on thinking vertically. Each app is its own stovepipe, and we're analyzing one app at a time. And I'm doing one, he's doing one, they're doing one. But the horizontal winds percolate up. So we did a study earlier this year where we worked with Sonatype, the guys who run Maven, and we looked at how a lot of people were downloading insecure libraries. So any win we can get there, that causes a lot of downstream wins. You fix a bug in a library, that fixes 1,000 customers rather than one at a time. So, what we did in this project was thinking horizontally, but it was a little different, right? Because we looked not only within a component like Commons Lang, we looked through all components, and we looked at the components of the components. So we looked at the encoding methods, right? So the encoding methods within each component, and identify how good they are and how bad they are. And some were bad, and we're going to follow up with that. And there's always going to be room for improvement in this type of research, and different directions we can go. But in general, I want to encourage the community to think more horizontally, and I think that's our call to action. So that's it. Thank you for your time. And if you have any questions, we're happy to answer.